Good evening, everyone. So, welcome back to another edition of our seminar series. My name is Aina Kauluma, and I'll act as your host and moderator tonight. And today we're actually joined by Johannes Lange, who is a business developer from GEO-NET, which is a wind consultancy firm. And he works in the international business development market. And Johannes Lange has 11 years experience in the wind measurement field, and he also has experience in several wind measurement campaigns in Southern Africa and worldwide. Johannes, thank you so much for joining us tonight, and I'll just hand this all over to you.
Yeah. Thank you very much, Aina, for the kind introduction, and thank you for the opportunity to speak here in this.
Hi, Johannes. I don't think we can hear you.
No? Oh. Can you hear me now?
No, I still can't hear you.
Yes, but we can hear you. Johannes, I think
okay.
the audience can hear you.
Yes? Okay.
Okay, let me just quickly give a call to Aina and let her know that we can hear you.
Okay, that's fine.
Thank you.
So, okay, the rest of the audience can also hear me, yes?
Yes, Lange, we can hear
Yes.
you. I can hear you from my side.
Okay, perfect.
I can also hear you from my side.
Perfect, thank you. Then I will just go on. And yes, I'm very happy that I've got to have the opportunity to speak in front of this audience and share some of the my personal experience in the field of wind measurement and the experience and the services we've done so far for the Daures project, which is a pretty nice example, by the way, for a nice measurement campaign. So I will focus in the second part of my presentation on this example of Daures. My idea was that I first give you a short introduction about what we do at GEO-NET so that you get a better idea why we have been engaged in this project and what we did there. Then I will show you give you just some general ideas about why wind measurement in general is so important and where in the whole value chain of developing a wind farm the measurement campaign is situated, and then just switch over and explain you what we did for the Daures project, because this is, as I said, this is a very nice example of how to conduct a measurement campaign, and I think you can learn most on this very concrete example in the Daures project. So I will just start the presentation now. 1 second. Oh, can I share the presentation, by the way? Here. Yes. So, can you see the presentation now?
Yes.
Perfect. So, short introduction about what we do. We are GEO-NET, a consultant for wind resource assessment and environmental metrology. We are active in this field since more than 26 years. So we've got like two departments. One is environmental meteorology. That's where our CEOs come from. That's their background when they studied in university, and we still keep this as one department. But the main focus of the company is wind resource assessment in all its facets. But we are quite focused on this. We are in the meantime, we are more than 60 experts from different fields like meteorology, environmental planning, engineering is getting more and more important, and geography, such as myself. The services we provide are wind potential studies, wind atlases, and wind analysis for like larger areas, wind measurement campaigns with masts and LIDAR, and then the actual energy yield assessment, which is basically analyzing the wind potential and then calculating how much energy you can get with a certain wind farm at a certain site. That's basically what we do for wind farm developers, and they need this energy yield assessment for their own calculations, but also very important also for the banks. The banks are requesting external consultants to do this energy yield assessment. We are doing this pretty much worldwide since the very beginning. This is a map with countries where we did projects, and you see it's like from north to south, from east to west, from Northern America to Southern America to Australia, Southeast Asia, Russia, and also in Africa. And the very first projects we did in Southern Africa was South Africa. Of course, this is still the biggest market for us in Southern Africa or in Africa in general. So big that we decided to create a subsidiary in Cape Town in 2020. And step by step, there have been more and more requests also from Namibia. Also some projects which we are currently conducting, a lot of measurement campaigns in Namibia at the moment. My colleague Ute Knör is currently in South Africa, and I think she just came back from a trip to Namibia for some site visits for MetMast installations. We hold an international accreditation for all our services. This is very important because that's what the banks want to see in the end. As I said, the banks request independent third-party assessments, and the accreditation we have guarantees that we are independent and that we stick to the relevant standards. The standards are also very important for the banks or a potential investor or somebody who wants to buy a project, that they can compare the results of our assessments with others. So this is the certification we have. We are members in several associations in Germany. We are also, that's not on this list, we are also a member at the SAWEA in South Africa, and member of the MESNET expert group in site assessment. This means we are not only applying the standards, but we are actively working in the relevant groups to improve the standards to meet the needs of our customers. Yeah, so much for GEO-NET. So let me now skip over and give you a short overview of why we put so much effort in measuring the wind. So first of all, I will present you the equation for wind power. I don't know if you've seen this before in the seminars. To be honest, I haven't followed the seminars so far. So please excuse me if this is something you already know. But it is so important because this actually is the reason why we do so much effort in measuring the wind. So what you see here is the equation for wind power. On the left side, you see what we want to know. It's the power, the wind power measured in watt. And if you multiply this by the operating hours of the wind farm, you've got the energy your wind farm produces. And that's the relevant information you want to have in the beginning. How much energy can I produce? is it a viable project? And on the right side of this equation is the information we have, or which we can measure. So we can't measure the wind power, but we can measure everything which is on the right side of the equation. So this 1.5, this is just a factor. This is rho, which is the density of the air, which consists of the temperature, humidity, and pressure. It's a linear factor, and in general, the air density does not change so much. It has an impact, but it's a few maybe a few percent, maybe 10%. It doesn't change much. This, the A, is the area of the rotor. And there you see, well, it's still linear. If you double the rotor surface or the rotor area, you double the power you have. And there you see, this is the reason why we are striving for larger and larger rotor areas. Because it seems to be quite easy. If you just double the rotor, you double the power. Well, of course, there are some limitations. You need to produce larger blades and they need to stand the forces. But that's another important factor, and it's linear. And this, the V, is the wind velocity in meters per second. That's what we measure with the wind measurement mast. And now the most important thing, this one. This is the third power of the wind speed. And that is mean. So the other factors are just linear. And this one is mean. This means the power of the wind changes with the third power of the wind velocity. So, like if you double the rotor size, you've got double the power. If you double the wind speed, you've got 8 times of the power. So, and that means in the end that small changes in the wind speed, which you measure, will have a huge impact in the power which you predict. And small error in the wind speed, which you measure, can have a large error in the energy yield assessment. And that can cause you ending up with a bad project in the end. So that's the reason why we put so much effort in. That's one of the reasons why we put so much effort in measuring the wind. Another reason is the wind flow itself. This is, sorry, I had the idea yesterday to put this in the seminar. That's why I just drafted it with a pen. I hope you can understand what I mean. In this sketch, I just compared the wind energy with solar energy. Solar energy is a much more linear source of energy. It's like if you shade half of the of the sun rays, you will get half of the energy in the end. It's quite linear, like obstacles just shade off the solar energy, but they don't influence the way the sun rays approach the panels. So solar is quite linear and quite easy to calculate object. Wind, in the other way, is quite more, it's pretty turbulent, it's pretty dynamic, it's pretty chaotic. If you've got a cliff like in this sketch, the wind particles which approach the cliff below will have to move around the obstacles, so they are forced to move upwards. And by moving upwards, they force the upper layers to also move upwards, which then again influence the layer below, the above and above and above. And so you
sorry, Johannes, you muted yourself.
So can you hear me now?
Yes.
Okay, sorry for that. When did you lose me? When did I start to mute?
The wind going over the hill.
Oh, okay, okay. So you did not miss much. That's good. Yeah, so in this characteristic of the wind causes the wind flow to be very dynamic, very turbulent, and very hard to predict and very hard to calculate. And then if you just see this, imagine how complex wind flow can be. And then imagine that that the wind speed influences the wind power with a third power, then you hopefully get an idea how difficult wind is to estimate and to assess, especially if you compare it to solar stations. Just to give you an idea, in PV power, usually, so first of all, you don't have standards like we have in wind power. Usually you just do simple online calculations, which is pretty easy, based on satellite data. Very different in wind. In wind, we need a thorough analysis. We need to follow the standards, and we need to have on-site measurements. So to somehow get a grip on this complex, turbulent, and dynamic thing, the wind, we do some to calculate how the terrain and how the area I have influenced the wind. We do we do a wind flow modeling using some very advanced computational calculation methods, which is called CFD, computational fluid dynamics. That's a way how to calculate how the wind is modified and altered by obstacles and by terrain. The model we use is called Fitna 3D. This is a very advanced CFD model. And it works like this, like in this picture. We've got input data from above. That's the so-called reanalysis data derived from satellite observations. This is data from a height of about 2,000, 2,500 meters above the ground, where the wind is considered not to be influenced by the surface anymore. And we use input data from below, which is the orography, the terrain, and the land use. And then this CFD model is calculating how terrain and land use are modifying the wind in the wind layers in between. So by doing so, we get a very accurate distribution of the wind, which means we can clearly say in this area of the wind farm, we will have more wind than in this area, for example. So the relative wind speed is very clear, but we don't have a good idea about the absolute value. That's one thing. And even worse is we can't give you an idea about the accuracy of this calculation. So we can't give you the uncertainties. And to calculate that, we need on-site wind measurements. The wind measurements give an absolute value, and we can adjust our model based on these wind speeds, and you can calculate the uncertainties. Aina, just a short question. Did you speak about uncertainties in the seminars before?
No.
Okay. So just a short excursus on uncertainties. If you develop a wind farm project and approach a bank or an investor to give you money for that, and you say, well, this is a very nice wind project. We've got 7.5 meters per second. That sounds nice in the first step, but the bank and the investor will say, yes, nice. But how certain are you that you will reach this 7.5 meters? And if you've got no idea about the uncertainties, you say, well, I don't know. And that's not enough for the bank. The banks want to know a value of the wind speeds which you are 90% sure that you will match that or be better than that. And to calculate this, how much is I am 90% sure to match that or be better? That's the uncertainties, or therefore you need the uncertainties. And that's why it's so important to measure the wind to calculate the uncertainties. So to sum it up, why we are doing the wind measurements in this way is we want to know the wind power. We only can measure the wind speed. And the wind speed goes with the third power. The wind power goes with the third power of the wind speed. And that means small measurement errors will result in large errors in the energy yield assessment. This, and because wind is a very dynamic and nonlinear phenomenon, is the reason why you need such highly accurate wind measurement data on site, and why you should be so careful about complying with the relevant standards. This can be the reason for losing a project or winning a project. So for wind measurement campaigns, the main objective is to validate the wind flow model we have, increase the accuracy, and, as I said, determine the uncertainties. The most important criteria for the wind measurement campaign is a high representativity, which means the measured data should be representative for all of the turbines you have in your wind farm. Second very important criteria is the traceability of the data. That means you need to be able to follow every step in the whole process of gathering the data, managing the data, and calculating with the data. And therefore, it is super important to get the documentation right. Like, it's nice if you build a mat mast on site, but if you don't have any documentation about what's installed on the mast, you will be unable to calculate the uncertainties later or calculate anything with this mast. Just a short example about that is you're measuring the wind speed and also the wind direction with the wind vane. And the wind vane needs to be faced northwards. So you need to know if you want to measure the wind direction, you need to know where the north arrow is. And we had a project from a customer. He wanted to have an energy yield assessment. He had wind measurement data and provided them to us. And I was looking at the documentation, and there was no hint about, there was a documentation about the installation of the mast and the direction where the wind vane was facing. It was north. And then I asked the client, well, which north is it? Because there was no documentation about, is it geographic north or magnetic north? And yes, there is a difference. And yes, especially in Southern Africa, it can be up to 20 degrees. So I asked the customer, well, which north is it? He said, well, wow, but which north? Yeah, is it geographic north or magnetic north? He said, what? Got no idea. So just imagine that if you don't have a documentation which clearly notes which direction the wind vane is facing, if it is north or like magnetic north or true north, you can have a change in the wind direction of up to 20%. So that's very important, traceability and the documentation of the whole process from installing the mat mast, gathering the data, managing the data, and all these things needs to be thoroughly documented. So the next thing is, as I said, low uncertainty. So you need to be as accurate as possible, measure as close to hub height as possible, and use calibrated sensors and follow the relevant standards. And bankability, that means you need to strictly follow the standards and provide documentation which complies with the relevant standards, because that's what the banks want to see. That's what is referred to as bankability here. If you miss that, and if there is, for example, if you don't have calibration certificates for the anemometers, or if you didn't note which north direction you were following, it's very likely that a bank will refuse an energy use assessment based on that. So that's why it's very important to just strictly stick to this. So to give you an idea about how a wind measurement campaign actually looks like, I would now skip to the example and show you what we did for the Daures green hydrogen project here. And this is the main objectives of the study we did. And as I said before, so in this case, we had at first we did a wind potential study to have a look at the wind potential. We also did the wind farm layout for the Daures project to define the turbine locations, and then to check to search for measurement locations which are representative for this turbine positions. And then in the measurement concept, we analyzed the terrain for complexity and elevation, defined the number and location of measurements to cover all the turbine positions. Then we choose suitable measurement mast and equipment, and determined the orientation of the mast. So to provide measurement data which are representative for the whole wind farm area, we need to look at the terrain complexity and terrain elevation. That's what we did in the first step. So the relevant standard MASTNet says in flat terrain, you can use one measurement location in a 10-kilometer perimeter. This is an example of a super flat area. And in complex terrain, you can only use one measurement location in a 2 kilometers perimeter. That's because the terrain alters and modifies the wind field a lot, as I described before. That's why you can only use it for 2 kilometers in complex terrain. So this means it's very important to know how complex your terrain is to determine the measurement locations. So in the first step, we analyzed the wind field. This is a wind field calculation with our FITNA 3D model. This is the initial area which was provided to us by NRSense. And when we did this calculation, we noted, well, in this southwestern area, it looks quite different than in the rest of the area. And we've got many areas with low wind speed, and it looks quite complex, actually. So you see that in the northeastern part, the wind field doesn't change much. That's nice. And it's quite high. And in the western or southwestern part, you see that the wind field is changing a lot, and there's a lot of areas with low wind speeds. So in the next step, it looks like it's very complex terrain. So in the next step, we analyze the complexity according to the relevant standard. And here you see the green area is the initial wind farm area proposed by NRSense, and the red areas are high complex areas. And you see that a lot of this initial area is complex, which means to cover the whole area, we would need to install a lot of met masts, which is a lot of effort, a lot of costs in the beginning. It will result in problems of installing the turbines, and it's very likely that you don't get as much energy yield as in the flat areas. So my colleague Ute, who was developing this, this study, then got the idea to just shift the area a little bit northwards. That's the blue frame, to get out of the complex terrain, get into flatter terrain, where it is way easier to do the wind measurement and way easier to install the turbines. And you've got a higher wind potential. So this is the wind field calculation for this new area. You see the wind is much more evenly distributed. You've got just a small area which is complex, and this promises a much higher energy use assessment. So this convinced NSENS to go for that area. They spoke with the community, they changed the area, and this is the actual wind farm area we have now. This is the initial wind farm layout we developed based on this wind field which we calculated. And based on this information, we then started to find the best location for met masts to cover the whole area. And therefore, we also had a look at the terrain elevation. It's interesting in this case, though the area is very flat, it has a slight slope. And the standards, MASNet and IEC 61, demand that to be representative for a certain turbine position, the difference in the elevation must not be more than about 50 meters. And in the end, it turned out that the whole terrain elevation is much more than this 50 meters. So we needed to find some places which cover the whole area. And we ended up with a proposal for 2 met masts. So this is the first met mast which we proposed. And in green, you see the area which is represented by this measurement. You see it's a kind of a circle. The circle is the 10-kilometer radius which MASNet demands. But it's not full. You see that there are some areas which are not covered in, which are not green. And this is excluded due to the elevation, because the elevation in the rest of the area is higher than the standards allow. So we needed to come up with a second met mast location to cover the rest of the area. This is the second met mast which we proposed. And again, it covers a radius of 10 kilometers, but there are some areas excluded due to the elevation. And now if you combine those 2 met masts, you see that you cover the whole area. There's somebody with the microphone on. Is this, do you want to ask something or? Okay, that's fine. Yeah, so that's how we came up with this measurement concept and the 2 measurement locations, which now cover the whole area and will provide for an accurate and compliant measurement campaign. So in the next step, we proposed a certain measurement mast setup. We decided to propose a 120-meter met mast. That should be sufficient in this area. And because it's flat and the wind speed is pretty high, so you won't need to go for high hub heights. And that's why 120, we thought 120 meter is sufficient. This is the setup we propose. You see a lot of anemometers on this met mast. You see a lot of anemometers on the same height. This is due to redundancy. The location is pretty remote. So if something breaks at the met mast, if one of the anemometers fails, it takes a lot of time to travel to the site and fix it. That's why we proposed to have as much redundancy as possible, so that if one sensor fails, you still have another sensor and it won't compromise the measurement campaign. We also have some measurements for temperature, pressure, and humidity to calculate for the air density. This is very important. Usually we propose 2 temperature measurements, one on top and one on the bottom. This is mainly because we want to get a good idea about the temperature difference in between the hub height and the ground. So, and in the next step, so that's the setup we proposed. And you see a typical met mast consists of a structure, the actual mast, and the sensors are carried by booms, which are installed to the side of this structure. And you can imagine that a massive structure like this will have an influence on the sensors, and this is something you need to minimize. Therefore, we need to find a good orientation that these sensors are not influenced or not much influenced by the structure itself. And this is what this picture should show. This is a view from above. So you look on the met mast from above. This is a met mast. This is a triangular lattice structure. And just imagine the wind is coming from this direction. Then these lines show you how much the actual mast structure changes the wind speed around the mast. So if you've got this figure 1.00, this means in this line, the wind speed is the same as without the mast. And here, like 0.696, this means that the wind speed has been slowed down in front of the mast. And here the wind speed is even higher. So you see the influence of the mast structure on the wind. This is the wake of the mast. This is a turbulent area where you measure anything but the real wind speed. So what you want to do is you want to stay clear of the wake and want to stay as far away from the mast as possible to get a most accurate wind measurement. And this should be the boom. And this is an anemometer. And this shows where you want to place your anemometer depending on the wind direction. You see, that means that you need to consider the main wind direction to avoid placing the sensor somehow in the wake or in an unfavorable position on the mast. This is how it looks on a tubular mast and just on a lattice mast. And just for the completeness, this is how it looks on a tubular mast. So the influence on the wind is a little bit different on a tubular mast, but still you need to consider the main wind direction and the influence of the mast on the sensors. That's what this drawing should mean. So taking this into account, we were checking the wind distribution. You see it here in the lower left corner of this slide. You see that the main wind direction is northeast. So this is the direction in which we want to align the met mast. And you've seen this here in this graphic, in this drawing. This is the main wind direction, northeast. This is the mast structure. This is the booms, and this is the anemometer. And you see that we oriented it in a 90-degree direction to the main wind direction. And you also need to consider the secondary wind directions. You see here, this is southwest to south-southwest. This provides still a good measurement with very low influence of the mast structure on the measurement. And it's a little bit different with this secondary wind direction, which is southeast-south. And you see that it's more difficult in this direction. So if you've got a sensor here on this boom, it will be shaded by the mast. It will be in the wake of the mast in this wind direction. So you need to make sure that you've got, that you have, that's also a reason why we've got these redundant sensors on both sides of the mast. Because if you've got this south by southeast wind direction, if you've got two sensors on one level, this makes sure that even if one sensor is shaded by the mast, you've got another sensor with which is free of the wake. Yeah, so that's how we decided how to do the orientation of the mast. This is an actual drawing of the mast, and it gives you an idea about the dimensions. And this is just to give you an idea how accurate and how complex the actual standards is, which we need to comply with. This is from the IEC 61400-50-1 standard, which defines how a met mast must look and how a measurement should be conducted. And you see how detailed the dimensions are calculated and drawn here. This, for example, this is the boom length of the secondary anemometers. And you see that the boom is 2.5 meters long. Just to give you an idea how far away from the mast structure we want to be to get rid of the influence of the mast. And this is the top anemometer on a huge spire, which is very narrow. And again, this is done to avoid an influence of the mast on this primary anemometer on top of the mast. So this is the sensors we install. Very important to have a valid calibration for the sensors and high quality sensors, which have a classification, so which are allowed for wind measurement campaigns. I think we are pretty much at the end of the seminar, so I will just give you the idea. It's very important to have a valid calibration and carefully handle the sensors. And this is how the met mast will look in the end. This is a sample photo. The masts are not installed yet, but we are close. And this is how a met mast will look in the end. So to give you the chance to ask some questions and start some discussions, I will end my presentation here, and I will give the floor back to Aina and the audience for questions. Thank you very much.
Thank you so much for your very informative presentation, Johannes. We're very grateful for the opportunity that you granted to us. And so I'll actually be opening up the floor to questions now, but to the audience. But before I do that, I'd just like to ask my own question first. So I see for the wind measurement campaigns, you have MedMast and LIDAR systems. So which one would you recommend for whichever project it is that you're involved with, and why would you recommend that specific system, that project? Because here for the Daures one, you recommended MedMasts. So why not the LIDAR systems?
This is a very interesting and very important question. I was thinking to include this in my presentation, but found that that would fill another seminar on its own. So that's why I did not mention LiDAR here. Yeah, well, in general, you can say LiDAR is using laser beams to measure the speed of the particles in the air. It's the same principle like the police uses when it catches me speeding. And in general, how can I say it? In this case, the advantage of the MetMast was basically the price. So exporting a LiDAR to Namibia, renting it, usually you rent it for a certain time. And the longer you measure, the more expensive the LiDAR will get. That is one reason. And a LiDAR needs more often some maintenance, like you've got a wiper which cleans the laser screen. It needs water, and I assume it can be quite dusty in the Daures region. So you need to wipe very often and refill the water. And traveling to the remote site is more difficult. I think that is the main reason. You can use LiDAR in the same way. It's bankable, it's accepted by the banks, it's included in the relevant standards. There are some projects where LiDARs have some advantages, especially if you go for very high hub heights. The LiDAR can measure up to 200 meters for the same price as in no heights. And building a high MetMast is very, very expensive. But in this case, with 120 meter, we considered the MetMast being more advantageous, having a better price to accuracy ratio.
Okay, thank you so much for that, Johannes. So I see in our audience we have Joseph Shiweda, who has his hand up. Joseph, you can unmute your mic and ask your question.
All right, Aina, thank you very much. I hope I am audible.
Yes.
Yes.
Yes, Johannes, thank you very much for providing a useful presentation to us. It was very interesting for me, and I mean, it just raised my curiosity in this wind energy area. Anyways, my question is very short, and I assume you are familiar with the terms that I will be using. So you were mentioning wind measurement. I want to understand what is the best resolution and duration for reliable information on wind region of a given area.
You mean the spatial resolution?
Not spatial, like measurement resolution. After how many minutes must your sensor record? Yeah.
Yes, that's quite easy. It's the relevant standards define that you need to have 10-minute data sets in the end. So the resolution is defined by the standards to 10 minutes, and that's definitely sufficient for the wind measurement campaign. So the sensors are measuring at, I think, 1 hertz, so at least one measurement per second, and it's aggregated and stored at the data logger at 10-minute averages. So you get the 10-minute average wind speed, the maximum wind speed and the minimum wind speed, and the turbulence intensity in this 10 minutes data set. And that's sufficient. That's like state of the art and included in the technical standards. I hope that answers your question.
Yes, partially. In terms of duration, do I have to measure for 2 years, a year or so that I can get something that is really reliable and acceptable by the bank?
That's also a very good question. The wind is, in the end, the wind is powered by the sun. The sun drives the wind energy. Yes, the sun heats up the earth, air rises, and that drives the wind energy. Having said that, this means that actually the wind is following the sun. The wind regimes are following the sun. Yeah, you've got and that means again that you need to measure at least one whole season, 1 year, to cover all of the different wind situations. So 1 whole year, the more the better, but 1 year is minimum.
Thank you.
Okay. Okay, so do we have any more questions from the audience? I don't see any more hands raised or any comments within the chat. And we have 5 minutes left of the seminar. So if you do have any more additional questions, please come forward. Okay, we see. Okay, and Dapa, can you please just unmute and ask your question? And then after that, Lucas, you can unmute.
Good evening, everyone. It's not really a question on the seminar presentation, but I want to ask something. I have received an email like yesterday from you guys to register to access the shared folder for the module second research Daures green hydrogen village pilot project. But I was struggling to register. So maybe Aina, can you tell me what to do?
Okay, Dapa, thank you so much. Can you just provide me with your contact details in the chat, and then I will reach out to you after the seminar so we can try to figure out what's wrong and how we can give you the information that you do need.
All right.
Okay, thank you. Lucas, your hand was up, but now it seems as if you've disappeared. So if you're still in the seminar with us, please ask your question.
Yeah, I'm still in. Good evening, everyone. Johannes, Aina, thank you very much for this presentation. Just a quick one. Johannes, in a fairly flat area with a consistent satellite wind data spanning over a region of, let's say, 50 to 100 kilometers, given fair and consistent data from satellite over a fairly flat area, can a certain station's data be used over a 50 or 100 kilometer range?
Not really. I would say not really. Because there is, due to this very turbulent and chaotic nature of the wind, even small changes in elevation or terrain, even if it's fairly flat, can have quite an effect in this distance. So if you want to use data in that range, in that distance, you will be pretty unable to calculate the uncertainties. So you can calculate anything, but you don't know how accurate it is. And as I said in the beginning, for investment, it's not important to know the so-called P50, like the average value. What the banks want to know is the value where you are 90% sure that you meet that or be better than that. And therefore, you need to calculate the uncertainties, and you can't do that in such a distance. Yeah, I can give you a value, but I can say, well, you can meet that or you don't. I don't know. And that's not what the banks want to know. Yes, I hope that answers the question.
It does. Thank you very much.
You're welcome.
Okay. I see there's another question from Wolf Richard. So Wolf Richard, you can unmute your mic and ask your question.
Yes, thank you so much, Ina, for the opportunity, and also thank you, Johannes. I'm listening from Germany, and Johannes, I think you have years of experience in this field and also access to a lot of data. My question is more like general interest. Can you detect an influence of global effects like climate change or other climatic effects over the past decades from in the wind measurements you do?
Yes. Thank you very much for that very, very interesting question. I really love this question because this is exactly what we are currently working on. There's a lot of research going on. We just launched a new service where we calculate the potential effect of the climate change on the energy yield assessment in the end. A very, very, very interesting topic. To answer your question, that is pretty simple. I just can say no. We can't see any effect of the climate change in the data so far. So that's very interesting. So far, the signal of the climate change is very, very weak in the wind assessment, in the wind data. And we can't see it actually in the measurement data we did so far. What we do now is there are some data sets for potential for the climate change in the weather conditions in this 2,500 meter height. As I said, this is the area where the wind is not influenced by the ground anymore. There is some data sets of what changes in these layers of the wind. And we tried to calculate how this influences an actual wind farm. The interesting thing is, so we are doing this kind of predicting the future or looking into the glass bowl and try to estimate how the climate change will affect wind farms in the future. And so we can't see it right now in the measurement data. We predict that there will be some effect in the future in the wind farms. But as I said, the signal is very, very weak, and it's very hard to determine for a certain wind farm if there will be more or less wind speed. Yeah, and you can't also say, you can't say it in general. It's very, very site specific. One site may benefit from the climate change, another one might lose just a few percent. Some others might have no effect. It's very interesting question. It's still a lot of research to do, and yeah, that's all I can say for now. I hope that that helps you and answers the question.
Yeah, thank you.
Okay, thank you so much, Johannes. I see that we don't have any more questions within the audience. So I think it's time to end this. So I'll just give you another word of thanks for joining us and for presenting to us and for answering all these questions. And also another thank you to the audience for joining us tonight. I hope we see you guys at our next edition for this seminar series. So thank you so much.
Yes, thank you from my side too. Thank you for inviting me for this seminar, and thank you for the audience for your interest and your questions. And if you've got any further questions later on, well, it was a lot of input, yeah. And if you go home and think about this and come up with some questions later on or tomorrow or anyway, you can always contact me directly, ask some questions via email or phone. And I think, Aina, you can provide my contact details also for the audience. If you've got any questions or anything you want to discuss, please feel free to contact me anytime.
Yes, and if you'd like the presentation, you can also just email me and I will share the presentation with you. I will just put my email in the chat. It's just aina@daures.green. And I will also provide you with Johannes' contact details as well in case you have any additional questions for him.
Thanks and good night.
Good night.